second day. So Daniel will give us lecture on long-range phase transition.
Yes.
Like phase transition and long-range models.
Okay, thank you for the introduction. Well, Nicole already talked a bit about phase transition in long-range systems. He mentioned the theorem, the Mernin-Wagner theorem, that states that you cannot have continuous phase transitions for dimensions 2 or less, unless you're long-range. And now we will see, for example, that you can also have discrete phase transitions when you're long-range in 1 dimension that we could not have it if you remember, which now I will remember you. So for all as to start with, I will talk a bit about the model that we all know and that we have 10,000 papers about, which is the Ising model. For the moment, let's write it as a short-range model. Nearest neighbor for the moment. Okay, I'll just write it to remember, but I guess everybody knows it. And then SI, this is a spin that can be either plus or minus 1, right? We have the typical model, I don't know, spins, some magnetic field that prefers to align them, and then some interaction that interacts if they're close by. Okay, so this can be solved exactly with the transfer matrix approach. Everybody knows it, I guess. If not, don't worry, because we don't need it now. But you can solve it, and you see that for the 1-dimension case, okay, you can solve it for the 1-dimension case with this transfer matrix. There is no phase transition for t greater than 0. You can only have a phase transition exactly when you have a 0 temperature, and this is basically because for low-dimensional systems, typically quantum fluctuations or fluctuations is the case. This is a normal system, classical, tend to destroy long-range order, so you never have any order. The spins do not align. How to see this very easily is this Payol's argument that I will recall a bit for completeness and because it will help us. Okay, so let me kill this for a second for this argument, because I want to see a continuous phase transition, and this usually induces the first order phase transition, so continuous. What is the ground state? So a state where all spins are aligned, or all spins align or the other direction, right? If this is positive, we had a negative, okay, which is the excited state when we create a domain wall, right? So some are aligned, some are disaligned, and again, of course, we can have them on the other direction. Okay, just to remember. How we determine if we have a phase transition? We look at the free energy, for example, which is the energy minus the temperature and the entropy. So let's look between these two states because I want to minimize my free energy, if I can minimize my free energy by organizing instead of being disorganized. Yes, let's remember which is the difference of energy between these two states. Very easily. Here everything is plus. Here suddenly I have a minus J because I have a spin flip. So the difference from a plus to minus is 2 times. Okay, easy. And now which is the entropy? This entropy is log of 2 possible states. Maybe I should remember that entropy log of the number of microstates. And for the other one, again, 2, but I can decide where to place the wall wherever I want, so I have an n.
Excited state.
Yes, sorry. Yeah, I'm very bad with notations. KB, I set it to 1, H bar to 1. If you say KB or an H bar, it's 1. Okay, just to remember this. I think everybody knows, but maybe not everybody remembers. Okay, so if you look at the free energy, which is going to be the excited state minus the ground state, we're going to get 2j minus t log of n, right? If I look in the thermodynamic limit, this term always wins unless temperature is equal to 0, which means I always lower my free energy, this is sub n f, by disorganizing my system. Entropy always wins, no phase transition. Okay. Only at t equal to 0. Good. But now the question is, what happens to, no, let me first do it now. 2D. Let's do it quickly. Okay. I have a system, spins, and then, perfect. Sum that, okay. Which is the increment on energy? Well, the increment of energy is always going to be proportional, if you think, to the surface, which will be also important to remember that it's proportional to the surface in these cases. Because why? Yeah, it's the place where I have a difference compared to the previous one. My Hamiltonian was local, yada yada. Let's say n, now it's going to be the length of my surface. And now, which is the entropy? Very complicated, but I'm going to do a super naive approximation that I say, okay, I am, let's say, this surface, which I'm going to think of a person moving, okay, and I arrive to a junction, so here, in between the spins. I can go either to this direction, or this direction. And now let's assume all trajectories will close, which is a shitty assumption, but let's assume this, right? So in this case, then, for 2 dimensions, I have 3 options whenever I reach one junction. So number of microstates is going to be 3 times how many times I have to take this decision? 3n. Okay? Generally, it's going to be z minus 1, n, z being the number of... Yes, sorry. Okay. Perfect. Okay, so now you see that the energy and the entropy have kind of the same, the same order. So can I minimize, is there a stable configuration where I don't want to extend my fluctuations? So these bubbles, instead of wanting them bigger, they become smaller. Let's think that I can, all the things were closing, so I can do n plus 1. I take this difference, and we get 2j minus t log z minus 1. Okay. Z minus 1, which is 3 for my 2D. Just for your knowledge, this gives you a TC, right, when this is exactly 0, which would mean that the derivative is 0, so you reach minima. It gives you a TC for 2 dimensions that it's 2 divided by log of 3. It's, j, right? I need to do it scale, which is 1.82. The real one is at 2.27, okay. But not that bad, no? I mean, it exists. Let's say that this argument is just going to tell you that for 2 good, for 1 not good.
Once the coefficient is known that 3, I mean, omega equal to 3n, the number of states that you get.
This was 4 for 2D?
Up there. No, so this is an approximation because
yes.
These won't close. So
I assume that all are closing.
yeah, the actual number will be less. So what is that number? Is it known? Like,
I mean, I think it's known, no? I mean,
I don't remember.
it's known, but I don't remember. But take it like this. The exact number gives you this one. I know that it's a very complicated proof, no? I don't know if it's also Merlin and Wagner, I don't remember.
Maybe Pions probably.
I don't remember now, but yes.
Depends on the boundary condition, fixed boundary.
Yes.
Periodic.
But since I only prepared this to give an argument, I don't look so. Okay. So now let's consider our beloved long-range interacting systems. and see, again, I set at h to 0, if this argument holds again. Okay? Wait, this is still, let me do it like this. Okay, and I think Nicole already presented it. This, I have to warn you that maybe there is a mismatch of notation with alpha and sigma with Nicolo, so forgive me for that. Okay, this is the typical I minus j. I put it to the alpha. Did I put it? Yes. If I is not j and 0 otherwise. So they all interact, right? Let's see. This is interacting, all of them. So it's not only a surface term now. Okay, I think, let me check in time. 12 minutes, okay, maybe we can still do a bit of this. So, what is going to be the difference between the energies? This, let's say, excited state again, and the ground state. So, and imagine this with this, with this, with this is the same here. This with this, with this, with this. This with this, with this, with this. The same this with this, with this, with this. Only the parts that involve region A with B, with region A to B are different, right? Because I have a change in sign. And now, believe me, okay, it should be like this. Let me fix I to be on the first half and J to be on the other half. N half plus 1 N. Okay, sorry, let me put again. Oh, well, no, let's put it like this. Okay. Now, if we want to take periodic boundary conditions, because at the end it's easier, or well, not really for these arguments, but for the entropy we need periodic boundary conditions. If not, we have some boundary effects that tells that the energy is not going to be the same. My definition of A minus J is defined as the minimum between. But okay, I will not do this explicitly. You can ask ChatGPT, Gemini. You can do it yourself. But I'll tell you that this becomes a sum like this. R equals to 1 and half minus 1, assuming n to be even. I can tell you a bit why. Okay. Why is this? Okay, maybe just remember that J. Why I have this factor of R? Because let's say distance 1 happens only here and only here. Never happens again in periodic boundary conditions. Distance 2 happens here to here, but also there's next one to here, that one. So the more distance, the more times it's happening. This R factor accounts for this. And this n half, it's precisely counted from half the chain to half the chain, which you have n half times this. I don't know if it's clear, but just believe me. You check at this sum, and what do you get? So, alpha equal to 2, I greater than 2. Where did I put it? Sum converges, this goes to 0. It means that this sum, it's a number. Difference of energy being a number versus the entropy being log of the number of particles. It dies, no pity.
Can you repeat that?
This argument.
Oh no, after that, what you said about entropy or something.
Ah, sorry. So let's do it like this. This implies is of order 1, right? Because this converges and this goes to 0, right? This is greater than this one. So it's converging. But we've seen that S, it's again, it's log of n. So when I do this argument that I did for the one-dimensional one, I have some number, now it's not 2j, but it's a number, who cares? And then one that scales with the number of particles, thermodynamic limit, no phase transition for T that is non-zero. Okay, now alpha equal to 2, I'm gonna get same order, same scaling. Let's forget about the precise numbers. I can give them to you, but okay. Is of order of log. And for alpha, between 2 and 1, I have some scaling like this. Did I put it correctly? Yes. Okay, just to say an argument that there should be phase transitions at some point. Now, quickly, I have 30 minutes for this.
Just stay between this.
Ah, yes, true. Sorry. Okay. So let's look at the easiest case, which is alpha equal to 0. Which is this. Why is this the easiest case? Because suddenly there is no notion of space, right? Let's recall the Hamiltonian. It's something where these I and j run all over. So all are interacting with all. This is the easiest case. Probably you solved it in your statistical physics course. I guess so, yes. But if you want, I was planning on solving it quickly to just introduce one thing and then I jump to the quantum case, let's say. Everybody knows this and the solution to this?
Will it take a long time?
No, 2 minutes. No, 5, I guess. Okay, then I do it. So, how we're going to solve this and all the fully connected models, and also it explains a lot why these fully connected models can be solved and what is the property that these models have, is by doing this Haber-Stratonovich transformation, which is nothing than an inequality like this. Okay? You can check this. Very simple, right? It's an inequality, mathematics. Now this one, if you notice, since it's fully connected, I mentioned to say something important. I forgot to say this. This guy, its energy is scaling as the number of particles squared, right? Because I'm summing 2 times the same. So usually what you do, what you have to do, and very important for what we see later, is you rescale it, which is the Cox rescaling. Whenever you have to introduce this Cox rescaling, the system becomes of the mean field universality class. And the way to understand this is kind of easy. Let's see this. For this is very easy. Particle 1, let's say S1, is interacting, you can see, no? It has, with this term. Right? Particle 1 there, you substitute I for 1, which is this precisely, is the mean field, no? I'm summing over all possible spins and dividing by n. It's an average. So that's why they become of the mean field universality class. Anyway, the partition function, which is the trace of e to the minus beta h, which on this discrete sum, it becomes summing all possible configurations. We're doing ferromagnetics, so forget me for this. I have to do this. But with this guy, I can substitute this part by this integral with a new variable, which is this auxiliary field. So this becomes And now it's linear with S. And this you know how to diagonalize, right? I compute the trace. This guy, I can take it out. If you have the trace of e to the ASI, this is your summable purple field configurations. Up is plus, down is minus, and you have n copies because you have n spins. And okay. Okay, this is maybe an exercise, but now believe me that it becomes this. Let me do it like this. If my handwriting is bad, please let me know. And now you see perfectly why on the fully connected systems mean field is always exact. Because you always get this factor of n on front. And then you know from mathematics that if this n, we're looking at phase transition, so thermodynamic limit, I take it to infinity, this integral is the same as, okay, some factor if you like, and the derivative second, whatever, forget about this. The important thing is this part. As evaluated at a single value of this auxiliary field, which is the one that minimizes the entropy, identropy, the action. Okay? Good. So, you look at this, you have the free energy. Now it should be. Maybe I'm going a bit fast now. Okay, well, let's, which is defined to be 1 over beta log of this F. And this factor, it's irrelevant because it doesn't scale like this one. Just let's leave it here, just to tell you, this partition function, if you remember, is exactly the same partition function you get when you take the nearest neighbor Ising model and you do the mean field approximation. But in this case, it's exact. Okay, this you know. And now we can, questions? So with this argument, the fact is that, think like this, if you have a theory that's local, having a defect in one dimension, the energy cost, because it's kind of local, it's not extensive, right? Doing a spin flip, creating a wall, it's going to cost you an energy that's a number. Even if alpha is, it looks like it's non-local because it interacts with all, but it's decaying fast enough such that effectively it's non-local. It's like local. So the energy cost is a number. But the entropy gain is super large. So then what happens is that you always prefer to disorganize if you have a tiny bit of temperature, no? Introduce a tiny bit of temperature, so kind of disorder into the, well, disorder, understand it like energetical disorder, to the system, and then the effects proliferate super fast. No, you prefer to disorganize. But now if alpha was smaller than 1, the system becomes non-local. So now you do say, okay, now creating a defect, like I did in one dimension, has an energy cost that maybe it scales with the number of particles, which we will later see. Now I will talk about ensemble linear. So now suddenly you can compensate the entropy gain by a huge change in the energy, right? Because just a spin flip is has an extensive energy cost. Think of it like this. I don't know if you know, but with this argument you say for 2 dimensions you have a phase transition. I don't know if you know, but there is another way to compute some things that tells you that after 4 dimensions the system is becoming mean field exact. It's the upper critical dimension. And what is the only difference? Not the only, but think of it. What is the difference between 4 and 2? This set that we were talking about, the coordination number. Suddenly one guy has, okay, there are other things, no, in reality, but one guy has 2 neighbors, the other has 16. It's not only this, no? I mean, there are, for one dimension, momentum and energy conservation, like there are other things, but you can intuitively think like this. One other intuitive argument, if you've seen, you sometimes read about the literature, you've seen these Cayley trees, which are these, you have kind of this, and then it separates 2, and then it separates 2, and then it separates 2. Okay? I'm not an expert on this. These systems are also being field exact. And it's kind of because they have a lot of, well, let's leave it there. I would like to see, it has the effective coordination number is very large. If you look at a tiny region, you make it a bit bigger, suddenly there are many, many particles inside. No? But okay, maybe this is not the best argument. So I jump into the quantum case, which is the same as the classical one, but I will give you a proof, kind of, hand-wavy proof that why it's the same. Okay, then I need the... Yes. Because the computation is very tedious, so... Valentine. More or less, yes. Okay. Oh, well, there is this. True. Okay. So, for what we've seen, long-range interactions at some point allow you to have phase transitions, even if you are in one dimension. Everything we looked at was a one-dimensional chain. But at some point, I mentioned that the energy was diverging, and we need to introduce this Keck's scaling factor to make the energy extensive. And this has also another physical implication that now we will see. I will talk a bit about the physics and then a horrible computation. But I think it's very instructive, at least in my opinion, to understand why kind of these systems belong to this mean field universality class, and basically, while this computation is going to be horrible, after you understand this, you will just naively do mean field or do Haber-Stratonovich in your daily life and will be able to continue and move on. Okay, so tiny recap again of StatFis, just to remember that at least how I derived it, and many people derived it in their bachelors, the canonical ensemble from the microcanonical. I would say the microcanonical is the one that is easier to understand intuitively. Is you say, okay, which is the probability that my system 1 is in a certain state, given that system 2, like my reservoir, is in another state. And you say, okay, basically, it's going to be the number of states. If now this is all closed in the microcanonical, number of microstates of 1 times number of microstates of 2, which is number of microstates of everything, right? So the probability, you say, okay, it's going to be this. This is a measure of the probability inside an energy window of E1, because now the energy is not fixed, really, in the canonical ensemble. And then you continue and say, okay, now let me substitute E2 by E minus E1, because it's only the total energy that's conserved if I am in the microcanonical, and expand this number of microstates as E to the log, which we know is the entropy, yada yada, and if E is much greater than E1, I can do this expansion do a Taylor expansion, and this I identify it as my definition of the temperature in the macrocanonical. We got the Boltzmann weight, right? Good. This is the probability that a certain state has a certain energy, as we know in the canonical ensemble.
So here we implicitly assume that the second derivative is positive.
Is?
It's positive, right?
I think so.
Yeah, because you assume that it is
Concave or
concave.
yes. But then, yes, probably. But my point was, and I already gave this talk, you already know everything, is that we also did another assumption, which was that this E2, which is the energy of this reservoir, was exactly the total energy minus E1. And if you remember now, I told you that if I have to rescale the thing, it's not going to be additive. Let's kind of see this. Okay. Let's see. If the theory is local, you create a defect. The energy of the defect, we've seen that it was sub-extensive, no? It's a number. It doesn't scale with the system size. But at some point, we've seen that this energy of creating a domain wall, it scales with the system size, and therefore the total energy is the energy of one system, the other, and the wall. We cannot neglect the energy of the wall. Which I think, okay. Okay, I thought I canceled this one, but just to say that, this was a slide, maybe I should not put it, to say that this thing of, for example, but let me skip it. Sorry. Okay, now we'll look at this model, which is a fully connected model, again. As I told you, one can also solve it, but I just introduced this extra term, which I could have done a different extra term, which is easier to compute, but since I already have the computations for this, I left this one. That will drive me a first-order phase transition for the things that later you will see it's important to understand. Anyway, what we were saying is, consider this model and imagine now that I have no external field. So it's a classical model. I'm just care about the orientation of the spins. And consider that now half of the spins are down and half of the spins are up. Which is the total energy? Zero, no? Because here I do the sum, 0. Here I do the sum, it's 0. But now, which is the energy of each subsystem? Not 0, because this is n half and this is n half for each subsystem. So you see that the cost of creating this surface was proportional to the number of particles. That's what I wanted to mention. Okay. Let me explain 2 ways to understand this problem, which one would be related to the exercise sheet we will do. Well, exercise sheet, I don't know, tutorials. Which is, you can either understand it as the single spins, that they want to align up or down or whatever. These are quantum, right, because we have the transfer field. Or you could say, okay, my Hilbert space is a tensor product of SU2s. I can use a different representation, and I could go to, for example, the total spin. It's a bit more mathematics, but in these terms of the total spin, this is just a sum. Okay. And then the only thing you need to account is how many times which is the degeneracy of your irreps. If you want to know, if you don't want to talk like this, is okay. Once I'm in a center total angular momentum, how many times it's repeated this which is the multiplicity, sorry. Okay. What I wanted to talk about of these ensemble inequivalence is that sometimes, because of this thing that we were talking about the connection to the canonical of the microcanonical, it can be that one of the partition function for the canonical and the microcanonical will give us different results, different phase diagrams, which is basically a fact of that we were non-additive. This picture, for example, the good thing is that you can think in terms of these total spins, and then by the fact that, as I was mentioned, you don't only have the representation where the total spin S or the Casimir is n half, but you also have 0, 1, 2, 3, 4, 5. Diskles-Gordon, everything very difficult. But so you have like a multiplicity, no, for each GS. Meaning that, for example, there is a kind of a notion of a radius. This guy is super degenerate. This guy is not so degenerate, but it has another multiplicity given by this number. I can give it later, and so on and so on. And when you compute these traces, what you need to do is not only sum about the orientation of the SZ, but kind of the radius of this sphere. Okay. To compute the partition function, since mean field is exact, what we first want to do, now that it's quantum, okay, let's look, let me go back 1 second. Okay. If this guy is not here, I can do the same as I did here, right? Let's say I do a Hubbard-Stratonovich that decouples the term that is power to the 4 because it's power to the 2 times. And then I do another Hubbard-Stratonovich that decouples the power to the 2.
If sigma x is not there, it's just a classical one. Because
yeah, sure, it's not quantum, right? But that's why I'm saying that, for example, here you take 2, you do 2 Hubbard-Stratonovich, you can do it. I never did it, but if you want to do it, you can do it. So first, what I want to do is kind of make it, be able to separate this term from that one, and then do the Hubbard-Stratonovich if you like, which I will do it a bit differently, but it's the same. How do I decouple these things? I guess you've seen, you do this kind of Suzuki-Trotter decomposition, which is basically if I have the exponential to 2 operators, I can divide it into many sectors, right? NS, no? So e to the 2a is e to the 8 times e to the a. So I'm doing this many times. That's why I have divided by NS. And since now these are very, very small, I can effectively commute them and just write it as the product of one and then the other one. Of course, I'm introducing an error. Of course, if you're a mathematician, then you should prove that this error is converging to 0 when you take these infinite sums. I am not, so I proceed as it follows. Okay, so perfect. Now, this allows me to disentangle and make it now classical, but I have many more problems, no? Because now I have many times the same exponential. In between each of these copies, now let me put an identity. Basically what I'm showing here is the path integral, if you know from Feynman, but I'm going to put an identity in between of these copies. Okay.
This is also what you do to map the 2D classicalizing to quantum with an extra dimension. So there is a proof, no, that says that classical quantum correspondence.
Yes, but then what you do, if I remember correctly, is yes, but you have it on imaginary time. I know this is also an imaginary time. Sorry, it's the same. It's the same. Yes. Okay. So let's maybe step by step. Here, initially have the term that was diagonal with Z, and the magnetic term that I want to decouple, the transverse term. Then I put many copies, p of this exponential, and of course I need to put divided by to be the same, such that then I allow it to disentangle. And now in between all of these copies, I put this identity, and this notation, it means that this is a sum over all possible classical configurations, right? I'm taking the basis, the classical basis. Okay, good to go. I think I repeated the slide, sorry. Okay, so now, sorry. Now this part then has become a product of a lot of the copies that I had before. And the only thing I need to ensure is that because I had a trace, I have many copies, I need to come back to the same copy, right? Because this copy and this copy is the same. This, next Trotter state, the last one has to be the same copy. Okay, good. Because these are classical configurations, the evaluation of this operator is very easy, right? It's just a number. It doesn't change the state. It's diagonal. But it's a number that, of course, depends on the configuration. Sums of plus ones, minus ones, and so on. And then, if you think, now what I had is like this path integral, I have changed it into a number that weights me according to the configuration I am, and this that rotates me in between each Trotter state, right? Because this is just a rotation. Now, this is a bit annoying because it depends on all these configurations, right? So what I want to do is also get it out of this sum. And a way to...
What out?
So this guy, right, depends on the configurations that I have here, on the configuration of each trotter step. But I don't want this to happen, right, because then I cannot, this is weighted by a weird number that I cannot compute, right? I cannot compute, this looks like I could compute it, right? But I cannot because it's weighted by a number that depends on the configuration. So how do I, if I now introduce like a Dirac delta, which also gives me a good notion of the order parameter, which is the magnetization, this guy now will only depend on M, and I just need to worry about the representation of the Dirac delta that I introduce as an operator. So let's see if okay. Let me, no. Yes. Okay, but I did there is a mistake here, sorry. Now, as I was mentioned, this guy doesn't depend on the configuration, but on M, right? Which is a number. But this term here, which I forgot to write, it should be inside this expression. Apologies for this. Because if now this term is in this expression, this I know how to evaluate. It's the same as we had before, kind of, but now I also have the transfer field component. And then I can just evaluate it. This is it understandable, this, or should I go slow? Is it? But it's clear that this guy now should be here to ensure that this M is the same as this. And now after doing this, I have this horrible expression, right? This only depends on M. And now, here I did it correctly, I have the guy inside, which ensures me that this M will have the same value as the configuration when evaluated here. This part, I can evaluate, right? Because you can identify it as a...
The last slide. Can you...
So, sorry, this part should be inside. I missed it, right?
Oh, yeah.
This term. Sorry, I missed it, and this is only M. Now, this is the energy substituted with M, which I have already divided by the number of particles, because as you can intuitively want, I want the N here. And now this is the guy that, since I forgot to put it, now it's correctly placed here. This, if you can identify it, is again a trace. It's basically, I'm doing nothing, the midfield, if you like. Right? Because now, it's again, this has been linearized, and I can compute it, and it's the trace of the following operator.
What is the small e times mz?
Which,
Is
this is the energy per particle, sorry.
Oh,
See, I put it an N outside, this capital E divided by N. I'm very bad with notation, I think I may be confusing you. But the idea is, now that I managed to linearize my problem, the only thing that I have introduced now is a new variable, which is my Haber-Stratonovich field. And the difference between this one and this one is that it didn't suffice to put only one. Right? Here, I placed only one because it was classical. But here I had to put an infinite amount because this alpha, so this lambda, there is for alpha equal to 1, for alpha equal to 2, for alpha equal to 3, which were all these Trotter steps. So I placed an infinite amount of them. But I still managed to do it. Everything until this point is exact. Now, the characteristic thing of these long-range interacting systems, as I mentioned before, is that they belong to this mean-field universality class. And this is a hand-wavy physics way to prove you that it is. Which, what does it mean if it's classical? It means that that my guy here cannot mix me in between these Trotter slides, right? If you think about it, classical means that everything is dominated by a single trajectory. And this guy was the one that was mixing me Trotter steps. So now, when I take... Okay, then the dominant contribution should be just a constant, sorry. It doesn't change with alpha, it doesn't depend on alpha. And a way to see this is, after evaluating everything, this horrible thing, the fact that I have always this n in front of the exponential yields me that when I look, yields that as we mentioned, everything is dominated by the saddle point. So when you look at the saddle point conditions, which are these ones, up to this everything exact, let's say, this M, and Mi means the M of each trotter step, depends only on the sum of the lambdas. So there is no notion of I here, right? So M has no I in reality, because there is no I here. It's being summed over, has no I. And if M has no I, by the other saddle point condition that I want to minimize the magnetization, lambda has no notion of the trotter steps. So everything this that was very horrible, that if you want I send you the slides and we can discuss it later, just to show you in reality that mean field is exact for these fully connected systems, even if I had this power to the fourth of the magnetization. Even if I now put extra terms, it's always the same. Okay. Now, I have like 13 minutes to say, okay, this is my exact partition function on the thermodynamic limit. How to compute the microcanonical one when it's quantum? You cannot, in reality, right? Energies are discrete. Sorry, this has no sense. A Dirac delta has no sense. If the E's are discrete, it's not a continuous function. But it's true that if you are on the thermodynamic limit for what we've seen of the density of states that Nicola presented, these functions tend to a continuous, right? So think of it like I'm taking an energy window that's very small, how many number of states exist there, and I'm just taking the energy window to be as small as possible. But always, first, you need to take the thermodynamic limit. You can do the same by introducing a notion of the Dirac delta, which, if you think about it, before I was introducing a lot of Dirac deltas for my Haber-Stratonovich field, I just placed a new one. So basically, the microcanonical entropy is kind of the same as the free energy with an extra new variational parameter. Same computation, same steps. We can check it later, but okay. And this supposedly is a calligraphic S of entropy. It's a bit weird, but and a reference to see everything that I've done basically in detail, although I like my better. Okay, when you have the phase diagram, you can check the phase diagram. This everybody knows, so I go quick, let's say. As we mentioned, the free energy I want to minimize, and I have two saddle point conditions. How do I determine the second order phase transition? When it's just a parabola, and when I determine the first order phase transition, when I develop three bulbs, because statistical physics, you know. You can just check. We already got it. This is the phase diagram for the canonical, when I pick the temperature to be 3/2, 1.5. Same for the microcanonical entropy, but first I need to also, okay, 3 saddle points, as I mentioned, one extra. But then also I'm fixing the temperature, which, as we've seen at the very beginning, was just the derivative of the microcanonical entropy with respect to the energy. And I can either fix it in the not magnetized, m equal to 0, or in the magnetized case. Okay, I have to now maximize the entropy. The first order transition point is this one, but everybody knows. So I have two curves when I develop this problem, because when I have ensemble inequivalence, usually, I'm not sure if it's universally, but it decouples into two different curves. And now if I put one on top of the other, you've seen that basically I yield two different diagrams, right? The three critical point is in a different position. In this place, the canonical ensemble would be magnetized, while the microcanonical will be not. Something is happening here. The physical interpretation I gave it at the beginning. Okay, these are just plots in reality, because I recycled this from a talk. But the main point to kind of, learn about in reality is what I think this lecture, the aim of this lecture was to understand how all of these that look very complicated, how to understand this, has yielded the classical, the mean fields, thermodynamic potentials, and why they are exact. I don't know if this was clear. This was for the exercise, I was going to propose to do, everyone does the same computation, which are a bit different. And yes, if you want, these are by kind of details, but once you have the partition function, it's just extracting phase diagrams and so on. It's kind of known, I guess. So you just look when to minimize the free energy. Okay. Maybe as a curiosity, we were talking, at the beginning, why the microcanonical and the canonical? Now let's think statistical physics. Yield different ensemble, different phase diagrams. Usually one is the Legendre transform of the other, right? And while these are one-to-one mappings, when one function is convex and the other is concave, if one of these functions that's supposed to be always convex develops a concavity region, basically the one-to-one mapping is lost. So really what is happening is that you're developing some concave region on the entropy, which when you take the derivative, what's giving you the temperature, just forget about it. You develop regions of negative specific heat, which if you remember from statistical physics, it's supposed to be impossible because you're giving energy to a system, but it's cooling down. Now, it may sound impossible, but if you think further in star formation, this is precisely what happens. I think there are some times when the star is developing that it's gaining energy, but at the same time it's cooling down. But gravity is a long-range interaction, so just to say that this happens in real life, and it's not to be surprised. And yes, okay. And I think I am finished in reality because these were just flashing kind of results, which is more for a talk than for a school. Just to say, this is, well, it may sound just an exercise for statistical physics, and then it says everything mean field. There are experiments now that they're realizing these fully connected Hamiltonians with some caveats. In reality, they're not fully flat, the interactions, but they're almost fully flat, and they're already observing that, it has been observed that for one-dimensional spin change, you can have this symmetry breaking. And again, it was not a continuous symmetry breaking, it's Z2 symmetry breaking, so even, no, this was to say for another thing, sorry. Okay, and this is everything. Maybe it was a bit fast. Should we do some questions now?
Because up to 4 the time. The session is for up to 4.
Up to 4?
Yes.
I was super fast. Okay, then I can continue. I have many more slides.
Okay.
Let's then.
Any questions up to this time?
I had a question. That Hamiltonian that we had, no, the one that we used, the sigma z squared, and this one, it has how does it have long range?
This one?
Yeah. Oh,
Because this one is a square, no? So.
oh right. So
Okay, I have enough prepared. I am not leaving you now half an hour without doing anything. No, because I was very nervous, so I prepared a lot of things just in case this would happen, and it happened. So, see, this basically, if you separate it, it was precisely the one that I have there, right? This works, right? This. I'm summing overall, it's precisely this one. And moreover, I have an extra term, right? I have a term like this. I, J, L, M, S, I, Z, S, Z. Okay? Okay, then let's continue. Okay, great, in reality. Maybe I'm going too fast, maybe. But let's skip this because I think this is more interesting. Okay, so let's go like this. Since mean field is exact on these systems, I don't need to do all this mess that I just did of this trotter. I find it useful because it's, I mean, from the path integrals, you know, no? Which is the classical trajectory, the one that minimizes the action, which is the quantum effect. When you are accounting that, okay, there is another also contribution from all other possible paths, what Feynman did in his lectures. What we've seen on the fully connected is that because of this n factor that we always get, everything is dominated by saddle point, which is saddle point is always the classical trajectory, the one that minimizes the action. So quantum effects are washed away. Now, let's see the same effect, although I will not give you the proof because it's very long, but I will just tell you that it's true, and you have to believe me, and I give you the reference, and if you want, you delve in it, but it will take you a couple of days at least. At least it took me a couple of days. So let's go to the picture that we had before, instead of thinking about these Trotter steps, this classical configuration, this imaginary time evolution. Now we're going to think about, okay, my system was this fully connected system, which in mathematics, we said mathematically I could split it and look it differently in terms of the total angular momentum S and the SZ. So maybe let's see. Just for, I guess this is clear, but just a picture.
I guess you can use this.
Veramente, true. Okay. So we have our Hilbert space, right? That is what? Our C2 to the n. Right? I don't know. It should be something like this, no? No, it's just a picture. When you think in terms of the tensor product of this and this, it's very complicated. But there is a transformation that would tell us that our Hamiltonian, no, this is going to be my Hamiltonian, sorry. This is the Hilbert space, to think different things. It's separated, right? As I was saying, the S equal to n half, this S equal to n half minus 1, and some copies. Okay. Which is the degeneracy of the maximally, this guy, maximal spin, it's also the maximally symmetric sector. Okay? So, for example, let's take, we know, no, that it exists the S equal to n half, and the SZ also equals to n half. How many ways can I arrange the spins to give me this state? This is this state. I don't know if it's clear. Just one, right? Okay, this is an intuition to explain why this thing. Now let's look at one that has an SZ which is not fully aligned. Okay? Okay. In the fully symmetric sector, this is what? Spin flip. Yes, spin flip. Let's do it like this. Spin flip. But since I am bounded to be fully symmetric, right, because this is fully symmetric, it's a linear combination of all, wherever I place this spin. But then I know, okay, so this explains that also this guy is non-degenerate. Okay, so the maximal spin, there is only one copy. This, we understand. But I know that there is a state, right, that also has this magnetization. Right? And if you think about it, I'm not a mathematician, so I only give intuitive arguments. This state has to be orthogonal to this one, no? So you could think it's a state that, for example, it's symmetric under all permutations of these ones and antisymmetric of this one. Now, it's a bit complicated, but there are many ways to make, I could make this antisymmetric, that antisymmetric, that antisymmetric, but they are all, not all of them are independent. This would be a thing of representation theory of the permutation group, which is a complete mess. But anyway, you see, if I remember correctly, that there are n minus 1 states that are orthogonal to this. Okay, just to... Everyone happy? Trivial. This one is trivial.
N minus 1 is trivial. It's not?
This one is trivial. Yeah, okay. How many, think like this, where can I play the spin? In n positions. One is this one, the n minus 1s are this one. Yeah, but when I put 2 spins, it's not going to be so trivial.
So you are asking that n minus some g. What is that combinatorial?
Ah, yes. It's also, for a spin 1/2 is easy to do. But I don't remember now the arguments. I know the formula of GS. But I don't remember now the intuitive arguments to see it. But okay, it's related to the, if you want, yes, it's a you can map it to combinatorial problem. But for example, if you would take, which, let's say I take, instead of a spin 1/2, a spin 1s, it's actually a combinatorial problem, but a different one, and much more difficult. I know because for the exercise I wanted to see if we could do one thing, and I could not do it with 2 days, so sorry. I don't know if we could do it in one. But just to say, okay. I just wanted to say that there are many. This is, like, it splits. Maybe it's more intelligent to compute kind of the partition function of this one, and just sum all of them, right? Let's exploit the symmetries of the Hamiltonian. So, the only thing I need to account, yes. Now, instead of this many-body problem, very complicated, let's compute the partition function of a single spin, but it's not a spin 1/2. It's a spin n half minus 1. And later we sum all of them.
Why this spin, if I have a single spin which is spin in half, the state of that is completely orthogonal to the n half minus 1 spin?
Repeat, sorry?
You said something like that this spin in halves, the state of this object is completely orthogonal to the spin in half minus 1.
And that this is orthogonal to this. Yes, right? So, okay, let's go. I'll do an easy. Let's take 2 spins. Let's do an easy exercise. Let's take 2 spins. Okay? Let's take 2 spins. Which are the states? This one, no? Okay? Now, there is the fully symmetric sector, which you've known, which is the triplet sector, which is the yes, I was going to put minus, thank God. And then the fully antisymmetric one. And then what I was trying to explain is, okay, this for 2, but I want to generalize this to many. I should have, I'm sorry that I don't remember. There is a very easy way to see which is the way to arrange the spins, like this GS that I will see later, but I'm sorry that I forgot. I thought I would not reach this. Okay, sorry. Now, okay. There is a paper by Lieb which tells you that the partition function, now for a single spin, macroscopically large, so this, let's say this SZ can range from n/2 to minus n/2. So we have n states plus 1. The partition function of such a, let's say, quantum problem, if now the radius of this sphere that I was talking about, so the total spin S, is large enough, you can substitute it by a classical integral. This is a paper by Lieb. How the proof goes I can tell you a bit hand wavy, let's say, is first you use the coherent spin representation, which is basically this state is all aligned in one direction, right, in the Z. But I could also take a basis. I can take a basis where I align them over all possible configurations, right, of this field. Take a basis. It's an overcomplete, right, because this one and this one are not orthogonal. But it's still a basis. It's like the coherent basis when you do the harmonic oscillator. It's an overcomplete basis, but it's complete. So it's important, it's complete, right? If I do this, then in the paper of Lieb, I recommend reading. It's cool, I like it. Just let me write it here. This quantum number, right, it evaluates to this one. It's a very hand-wavy argument. So basically then Lieb shows that the partition function of this guy can be bounded by the classical partition function of a rotor moving on the sphere when the radius of this sphere is fixed to S as the lower bound, and where the radius of the sphere is fixed to S plus 1 as an upper bound. So now if I take this S to infinity, a 3D rotor. I said 2?
No, you said rotor, but...
Yes, a 3D rotor. Now I have 2 angles.
Yes,
So if now I take S to infinity, basically it's the same. Okay? So now, then, step by step, as I said, this is the classical partition function. So I substituted this, I don't have it here, by a rotor, and now let's assume that from this S, the partition function is just dominated by the S that are large, which in the thermodynamic limit, it's all of them, right, kind of, or trust me there. So then I substituted the integral, so for a fixed radius, an integral over the solid angles, and then I need to integrate for the radius from 0 to infinity, right? Which is this ts. S is kind of the radius. Instead of all this Trotter decomposition I show you, now you can do this, which is much easier, right? Because just take whatever is Sz, you put cos. Whatever is Sx, you put sine. But I think it may be complement, so I thought it was interesting. And for the microcanonical, same as before, just choose a representation of the Dirac delta. If you want, and you could do it as an exercise, you could put a Dirac delta representation that does not need to be the Fourier one that I placed. You could put a Gaussian. It will give you the same. I checked this. Okay. Now, the only thing we should worry about is how to express this GMS in the limit of S being large, well, so of the number of particles being very large, and is this expression here, which maybe I should show. How does it come from? Okay, so this GS is 2SS plus okay, this is N half N S. Now just do the approximation. Okay, now in my partition function, I have GS multiplying, but I want everything on the exponential, right? Because this part here is on the exponential. So I'm looking at log of GS, right? This is some n factorial and so on. Log of n factorial, where you can use the Stirling approximation. And the S now is parameterized as N half S. I'm sorry for this. because I left an M somewhere which is not correct. But just believe me for the moment and let's jump to the physics of it. Okay, so perfect. This expression is great because I have the energy, right, which I come, as I said, from solidifying this classical integral, which is this energy, and the entropy, it's coming for free on the partition function because it's coming from the degeneracy GMS, right, which came here in this factor. So I have perfectly the form of the free energy being the energy minus the temperature, the entropy, times the entropy. So even from the first expression, if you like, I don't even need to compute the second, I get the free energy and the entropy. Super easy to see. I'm sorry this I didn't prepare, maybe on the exercise I quickly do it.
I have a doubt, like, won't there be additional like 2s plus 1 factors that like GS?
Two.
This is like for a particular spin state, there are like 2s plus 1 like spin states, like degenerate states will be there in a particular spin.
So the degeneracy, so it's captured by the GS, which enters as the entropy.
Yeah, like in this formula, like ns like plus here, like in the board.
In the board.
Yeah, there will be like 2s plus 1 like factor, additional factor will be there.
In this one, no, this is already the degeneracy for each sector.
Yeah, but in each sector, like there are like 2s plus 1 like.
Sure, but wait, but yes, but these are not degenerate, right? Okay. In each sector, you have the 2s plus 1, which are the different SZ, if you like, right?
Yeah.
So, let me go one moment back. With Lip result, I substitute this sum by a classical integral of the theta and phi. And now, when I say, okay, these in reality only hold when S was large, right? S is large, then it's fixed to be large. So now, these guys, I do this Stirling approximation, and I substitute by this factor that enters here. Okay? Now it comes the thing that you can criticize. Okay, but then you're forgetting, if you want, about all the total spin, total angular momentum that are not proportional to the number of particles, which is true. I don't deny this. But now I will show you which is the phase diagram that this yield, and it's the same that I showed you before. And I'll explain you why you can see that in this case at least it's good that we neglect this. It works. So, okay, this was a color plot, sorry. Ah, no. It's finishing here. My bad. Sorry. Okay. Let me now tell you. I say it with words, sorry. I'm sorry.
Can you give a little bit idea how this GS is operating?
The GS. Okay. Let me go 1 second. Okay, it is a disaster. Wow. Okay. 1 second. Okay. You want to see, which I erased it, I don't know why this, okay, where does this come from? Now I need to remember though.
It's like simple if you look in terms of commutator. Like it will be easy like if you look at it in terms of commutator.
Up there?
Can I come and say that?
Yeah. I used to know this, Ah, you mean expanding it?
Not expanding, it's simple for me to. Suppose like if you have n spins,
Yes.
and, let's like look at particular like Z sector, which means like you have like like k upspin some n minus k downspins. Suppose if you want like for example sz sector, like sz equal to 0, so which means like it will be n and it will be like n by 2 and n by 2. So total number of states like will be like so you guys understand this formula, right? So in
Yes,
terms of
I know.
n spins, like you can rearrange, like there are like n c n minus 2 combination for all like these type of rearrangements. Understand this, no?
Let me think 1 second. So,
Okay, so like you know like
yeah, no, I remember.
yeah.
Okay. But yeah, okay.
It's like
Okay. Should I continue? I mean, I still have to teach, no, for 10 minutes. I'm sorry for this. This was a bit of a disaster. Okay. Okay. Then let me do one. Let first. Any questions up to here?
So I have a confusion about this sector dimensions. You mentioned that for s equal to n by 2 or s equal to n by 2 minus 1 and so on. So if we go downwards, if we just if we ask for what is the dimension of sz to be n by 2 minus 1 or something, then there are many states that are orthogonal, but if I just lower the spins, then this n by 2 is the lowest subspace, right? I mean lowest block.
Repeat, sorry.
I'm saying that this s equal to n by 2, this block,
Big M, big S, N2, or what?
s equal to n by 2, and if you flip magnetization to n by 2, this is the lowest block. Yes. Only one.
Yes.
Then, yeah, but then if I put the lower blocks, they have higher dimensions.
So, well, yes, this has the degeneracy, which we said it was n minus 1.
True.
The other one, it was something like n minus 1 times n minus 2, I don't remember.
Right.
Squared by 2n squared, yes.
Right. And this GS is the, as you tell, the degeneracy, and this is.
Is the degeneracy of each sector. So this formula, if you look at it, is take S and put n half.
But here, when you put s equals to n by 2, the second term becomes
It's 0, yes, this is 0. Because the binomial of n divided by n plus 1 is 0. So I put s equal to n half. This is the binomial of n divided by n, it's 1. Minus 0, it's 1. I put the n half minus 1. This is going to give me n minus 1. And then the next one is something like n times n minus 1 divided by 2. But okay, I'm sorry for this. I thought it would take much more time. Let's keep on questions. I think this I will save it for the exercise, one thing that I have here. Any more questions? Maybe regarding this, because I also didn't got it so much. I used to know this.
These kind of Hamiltonians, like theoretically it's interesting, but like experimentally, are there systems which we can study?
Well, as I was mentioning there, for example, they can make it on the lab. Basically, how it comes, I should maybe have prepared this slide. But basically, on cavity systems, you can create these patterns. Think of it like this. Okay. Sorry. Okay, so when you have these cavities, right, you can create with this standing wave like a periodic potential, right? And then you can, let's say that you have a spin degree of freedom in each of these. Now, you have this perfect potential by the fact that you have some interference, right, because the wave is an standing wave that it's reflecting and so on. So say that this spin moves a tiny bit to the side, then if it interacts with the light, it messes with the light, right? So suddenly just this guy moving a tiny bit changed the potential everywhere. So you can think that this guy moved a bit and everybody felt it. And then it surprisingly, let's say when you have these spin-light interactions, when you integrate out the degree of freedom, which is the light, not only you get a fully connected, but you also get the Cox scaling factor.
The 1 by n.
1 over n. Now, also I should say, in these cases, for example, this Jij, it's not exactly, I don't know exactly why, but they tend to this. Something of this form, if I remember, which when you take n to infinity, it's flat, but it's not really but it has an exponential decay, so it's staying on the strong long-range regime. Now, okay, what I wanted to say, that maybe, let me say it at least with words, because I don't have the slide. Okay, now, why doing this? So both systems yield the same phase diagram, both techniques, okay? But you could say that in this case, as I was mentioning before, this approximation of substituting this by a classical integral only worked when S was large enough, okay? So then why should be the same? The one before kind of was self-consistent, everything worked fine. I didn't do this approximation, but in this case, I did an approximation, right? I forgot, let's say, about the contribution of this nucleus of the sphere. But see, again, similar to well, in the same manner as the case before, I have a classical free action, right? And I have this n factor here, which also comes from the degeneracy of the spin states. So everything is dominated by a saddle point, which means that, again, just one out of all these integrals, there is only one fixed point that is completely dominating all the values. You could check that when you do the saddle point conditions with the m's and the s, everything is the same. But then you check, no? This s, which is a variable that's integrating from 0 to 1, which stands for the radius, it's fixed to a single value, its contribution, right? As I mentioned. So basically, as long as this s on the saddle point condition is not 0, it's 1, well, not going to be 1, but 1/2, it means that everything was dominated by a state that had a total spin s, which was proportional to n. One thing to learn from this expression, so I'm safe in this regard. Another thing to learn from this expression is that the entropy is only dominated, it only depends on S, right? There is no notion of the solid angles here. So it means that, and now I do a picture. Okay. Say I'm looking at the zero temperature phase diagram, or microcanonically, I fix the energy to be as low as possible, and I by the saddle point condition or by the fact that I'm at 0 temperature. Everything is dominated by a single state, which was here. And now say I increase the energy, right? This expression is telling you that the entropy only depends on which layer of the sphere you were. So this is a ground state. Okay. And now I don't know, I increase my energy and my state is dominated by this one, which is greater than the ground state energy. Okay? So the entropy only cares about the radius of this sphere because this g of s is growing exponential with the number of particles. So even though there are some states with the same energy as E around here, this layer of this sphere, this state has such a high degeneracy that it completely dominates the entropy. And as long as this is not basically on the core of the sphere, my classical computation was exact. And I'm very sorry for this. We'll talk it after the break. I will look at it 1 second. Thank you. Questions?
Do you know when you encounter this S3 or 4 terms in Hamiltonian?
If you encounter them.
Where do you encounter them?
In this case, it's a bit artificial. I mean, we just placed it to talk about this ensemble inequivalence. Because as I was mentioned, we need a first order transition point. So I placed this. But for example, if I would put a linear term with Sz, I can also induce a first order transition. I haven't checked, but I believe that there should be also a ensemble inequivalence. But let's say that in this case, everything was just merely artificial to show you and explain you a bit the physics about the ensemble inequivalence. They say that they can do it. They haven't done it yet.
No, so there is actually an experiment
Did they do it? I didn't know that.
I would consider it rather natural. If you have a parity invariant model, it would be the next thing, and I think that you can put there. So it appears not so unreasonable, I would guess. You can question whether you like non-local operators. That's, but once you accept that there is an m squared, for me it's not a big problem accepting also the m to the power 4.
Do you think this was useful? You think now you could do a computation, the same computation, let's say? We will try later.
We'll have a tutorial type of thing.
I prepared also, yes. We'll do a bit less. I think Giacomo will do.
Yeah, we'll just finish shortly what we did yesterday and then you're already in charge.
So any other questions? If not, so then let's thank the speaker.